Welcome back. I'm Lisa Blackburn. This is my YouTube channel of everything I want to talk about, science and math. And today we're in AP Chemistry talking about the gas laws, which are good to know. You can use them everywhere you go. Y'all remember the gas law song? PV equals nRT. See, if you knew the song, you'd know the formula. Okay, so we got these two balloons. One has hydrogen and one's got oxygen. They have the same volume, and we were talking about these balloons, and now we're moving forward. So each gas sample has the same average kinetic energy because they're both at the same temperature, okay? Are the molecules in each balloon traveling at the same average speed? So is hydrogen molecules traveling at the same average speed as oxygen molecules? Yes or no? What do y'all think?
No.
No. Can you tell me why?
Oxygen molecules are bigger.
Oxygen molecules are bigger, yes. So it's not the same speed, it's the same average kinetic energy. And if you remember from physics or physical science, when you took it in 8th grade, kinetic energy equals 1/2 mv squared. Remember that? Mass times the velocity squared. So oxygen has a bigger mass, so it's going to go slower, but it'll have the same kinetic energy. Where helium or hydrogen, that's what we got. Hydrogen is smaller, but it has to move faster to have the same kinetic energy. Does that make sense to you? Can you see it? So the answer is no. Oops. Draw. Doop. 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 No. So they have the same average kinetic energy. H2 is smaller, lighter, less mass, faster. Okay, do we feel pretty good about that? Can kind of imagine that? Now, consider each of the following situations and decide whether or not certain variables will increase, decrease, or remain the same. Assume that the amount of gas is constant. Okay, so first of all, we have a sample of gas heated in a rigid container of constant volume. What's going to happen to the pressure? You heat it up, it's in a container, what's going to happen to the pressure? Increase, decrease, or stay the same? Increase. That's why you don't throw an empty can on a fire, because it's not really empty, it's got gas inside, and it'll explode and kill you. People in Georgia have killed themselves not knowing that. What will happen to the density? It's sealed. Can particles get in and out? No. So the density is going to stay the same. Okay? The average distance between the gas particles should stay the same because you still have the same number in there and they're going to repel each other and spread out. The average speed should increase, decrease, or stay the same with you heating it up? Increase. Great job. Okay? A sample of gas in a cylinder fitted with a movable piston. The gas volume is reduced from a liter to 1/2 liter at the same temperature. So now we have squished it down. But when we squish it down, what's going to happen to the pressure? It's going to increase, right? You squish it, it's more pressure. The density of the gas should... You're squishing it more? Yes, it's increasing. Very good. The average distance between the particles should decrease because now they're closer together. The average speed of the gas particles, notice it's at constant temperature, so what's happening to the speed? Nothing. It's going to stay the same. Good. A sample of gas in a rigid container at constant volume. Now we're putting extra gas injected into the container. Okay, putting a little more in. So what's going to happen to the pressure if we squirt a little more gas in there? Increase, right. What about the density? What's it going to do? It's going to increase. We got more molecules in there now. The average distance should decrease. They're closer. There's more people. There's more molecules in there, like people in a concert. And notice that it's constant temperature. So what's going to happen to the speed? It's going to be the same. Very good. Okay, 10-4, the ideal gas equation. PV equals nRT. Okay, so it is written. PV equals nRT. That was pretty easy. If we use a value of 0.08206 for the gas constant R, we have to make sure that the pressure is in units of atmospheres, ATM. Now, there's a whole bunch of different units for R. But it appears from this and what I've read that on the AP test that they only do two. This one and that one. So the units for this one, the pressure is in atmosphere, the volume needs to be in liters, and in all gas laws, what does the temperature have to be in? Kelvin. Very good. Okay, if we use a value of 62.36 for the gas constant, the only thing that has to change is the units of pressure, which become torr, or millimeters or mercury. Remember, they're the same. They're both 760 equals 1 atmosphere. Okay, so now let's do a problem. Use the ideal gas law to calculate the pressure inside a helium tank that has a volume of 17.8 liters and contains 30 grams of helium at a temperature of 22 degrees Celsius. What do we need to do very first on all of these problems?
Rearrange the equation.
No.
Change the temperature.
Change the temperature to Kelvin. Always do that first, because if you do it wrong, you're going to get it wrong. You always got to do that. So we do plus 273, so that equals 295. So very first thing, just get it in your head, get it out of the way. Then the other thing is PV equals nRT. Do you see an M in PV equals nRT? No. And we have grams. So what do we need to change those grams to?
Moles.
We need to change them to moles because moles are in it. N is moles. So we should go ahead and do that, change our 30 grams. So we'll do it over here. 30 grams, and it's helium. So what goes in the denominator down here? 4, which is the molar mass of helium, right? So it's 4 grams per 1 mole. So now we've got it in moles, which is 7.5 moles. So this is just sort of our pre-work, getting everything ready to go. Now we can do this. Now, somebody said what we need to do next is rearrange our equation for pressure. I don't do that. I like to put my numbers in first and then move around the numbers instead of moving letters. Some people like to move letters, the physics teachers here at East. I like to put mine to go ahead and substitute first. And I sing the song, Substitute by The Who. It's from before my time, so I know it's before your time. Okay, so our volume that they give us, 17.8. Our number of moles we solved for it is 7.5. We have our pressure is what we're solving for. And we're going to use for R 0.08206, which means we'll be solving for it in atmospheres, and our temperature is 295. So what I would do on my calculator is 7.5 times 0.08206 times 295, enter, divided by 17.8, and pressure equals 10 atmospheres. Put a box around it. That wasn't too hard, was it? But do you see how that's different than when we had these problems in honors? In honors, I would just flat give you all but one variable and you solve for it. In AP, you often have to do a little something to get your variables before you get to solve it. Okay?
How
What?
did you get the 0.08216 again?
It might be rounded to sig figs. We got 22 degrees Celsius. You got something a little different than 10 atmospheres?
Oh no, I was wondering how you got the R.
Oh, the R is the constant. I got it higher up in the notes there. Scroll up. And It's one of the two. You're either going to use that one or the 62 one, depending on what units they give you for pressure. Okay, so next one is the combined gas law. P1V1 over T1 equals P2V2 over T2. And they want us to solve this problem. We have an inflated balloon that has a volume of 30 liters, that's V1. At sea level, 1 atmosphere, that's P1. During its vertical ascent, the temperature changes from 25, that's T1, to negative 19, that's T2. And the volume of the balloon increases to 55, that's V2. What is the atmospheric pressure, P2, when the balloon has reached the higher altitude? So we have everything but P2, and we can substitute it in. So I'm not going to rewrite it. So my first pressure is 1 atmosphere. My first volume is 30. Now, we need to change those though. 25 degrees Celsius is equal to 298 Kelvin, and negative 19 Celsius is equal to 254. So always remember to do that. So over 298 equals, my unknown is P2, I'll put P2 for my variable, times 55 is my final volume, and my final temperature is 254. So if I was going to do this problem, I'd do 1 times 30, enter, divide by 298, enter, then I would multiply both sides by 254 to get that out of the denominator. So then I'd do times 254, enter, divide by 55, enter. And so pressure 2 equals 0.46 atmospheres. Not hard, that's a P. I know it looks bad. How do we feel about that? Lara, are we good? Okay, good. Okay, moving right along. 10.5. So here's one where they want, sometimes you have to deal with density, and this time they want us to just rearrange formulas. So density equals mass over volume, you learned that in physical science class. Show how the density, or physics, show how the density equation can be converted into this. So we're going to rearrange it to that. They use big M for molar mass. I do 2 lowercase m's. They do 1 big M. I don't use 1 big M because 1 big M means something else in chemistry. What does it mean? Molarity. So I don't like this, but you know, I'm being flexible. Again, they want us to use PV equals nRT. Now, this is no numbers. This is just rearranging equations. So we're going to have to do that. Okay, so first of all, we're going to rearrange this to volume because what they want us to do is deal with this equation. So volume equals nRT divided by P. Everybody good so far? So now I can write this formula. Density equals mass over volume, but volume is nRT over P. Okay. We good so far? Okay, so the next thing is that, did I draw that there? Okay, so here I have mass over number of moles. Everybody see that? And that is the same thing as big M. Okay, do we feel all right about that? Do you see how I could pull that out and put a big M in the numerator? Moles, molar mass divided by number of, mass divided by number of moles, okay? And then the other thing I want to do so that I can get this is notice that P is in the numerator here, and here it is in the denominator of the denominator. Everybody see what I'm talking about? Okay, so I call this, when I teach math, the first will be last rule, okay? So there's a saying that the last will be first and the first will be last. Well, I just imagine that if I am a number, the very last place I want to be is in the denominator of the denominator. That seems like a humbling place to be for a letter, or a number, right? So this is a rule in math, and it's on the SAT. They love this rule, and to see if you know it. If something is in the denominator of the denominator, it gets to move up to the numerator. Did you know that rule? So you can just put in your head, the first will be last, the last will be first rule. The little p gets to bump all the way up to the numerator. And this mass n is m, and RT is still in the denominator. Yes?
Isn't it just keep, change, flip?
That is one way I look at it, yes. But some people get confused by that. This way, you don't even have to think that. You just go, oh, boop, up it goes. That quick. Boop, up it goes. All right, so now we're going to rewrite it. Mass over number of moles is equal to big M. P gets to move up to the numerator, and then RT is in the denominator. Ta-da! So we did what they wanted. They wanted us to think about these equations and how we can move from one to the other. Okay? I don't think that's going to be on the AP exam, but maybe it is. Maybe they're going to have you manipulate some equations, show that you know some math. I think they're more likely to do something like this. The density of dry air at STPs. Okay, so do y'all remember STP? It's on our box. It's 0 degrees Celsius and 1 atmosphere. Okay, everybody remember that? Okay, so the density of dry air at STP, so that's 273 Kelvin, is 1.29 grams per liter. What is the density of dry air at 100? Okay, which is, so that is 373 Kelvin, assuming that pressure remains constant at 1 atmosphere. Okay, so we are given grams per liter, we're given density, and we need to get from that, because what we want to do is we want to use a law, V1 over T1 equals V2 over T2. Whose law is that? Charles. Ooh, yes, some of y'all got it. V1 over T1 equals V2 over T2. But we don't have that, we got a density. So we need to do a little converting here. Okay, so our density is 129 grams per liter. And what we're going to do is, what we're trying to get here is density again, but we have this instead. So what we can do is we can fill in all of this and we can get our new volume, and then we can get our new density, because everything else will be the same. So to start off, what is our original volume? Those grams per liters. How many liters? One. You see where we got that? So 1 liter is our first volume. Our first temperature is 273. Our second volume is what we're looking for, and our second temperature is 373. So X, our new volume, is 1.37 liters. So our grams per liter are 129. Our grams have stayed the same. We just have a new volume. So we can do our density. Density equals 129 grams over our new volume, 1.37 liters, and we could get our new density, which equals 0.94 grams per liter. So that is V2. Do you see how I did it? Last time I jumped ahead of myself. I'm using restraint. I'm waiting till we get to the next question. I answered it before we got there. Does this seem logical based on what you know about hot air balloons? Okay, so it got hotter, and did the density go up or down? Down. Is that logical based on what we know about hot air balloons? Yes. Yes. Because it is less dense when it got hotter, and less dense things do what? They float, right? They rise. So yes, it is logical. The heated up, it got less dense. Can I scroll on to the bottom? Next one. Okay, this one's a little complicated, but I think you can do it, and I think it's going to be encouraging to you. Okay, this is an actual AP test question from 2009 that has to do with this. Okay, so this is great. You get to see a real AP chemistry exam. So let's go through it together, and hopefully you'll go, oh, I could have done that. A student was assigned the task of determining the molar mass of an unknown gas. The student measured the mass of a sealed 843 milliliter rigid flask that contained dry air. The student then flushed the flask with an unknown gas and resealed it, measured the mass again. Both the air and the unknown gas were at 23 degrees Celsius and 750 torr. The data for the experiment is shown in the table below. So, before we even look at that, we should change that Celsius to Kelvin, shouldn't we? Step one, so we don't forget to do it. Now, it would have been very smart of this student to have gotten the mass of their flask before they started the experiment. But they didn't. So we're going to have to work around it for them. They've got the volume of the sealed flask, that's the volume, the mass of the sealed flask and the dry air, and the mass of the sealed flask and the unknown gas, okay? Calculate the mass in grams of the dry air that was in the sealed flask. See, that would have been easy if they had just gotten the mass of their empty flask. The density of dry air is this. That's the temperature, and that's the torr, okay? So, what we're going to do is our density, oh, here's another little thing I want to point out to you. What does it mean, L to the negative 1? Inverse, so what does that mean? Where is that L? It's in the denominator. So they could have put grams per liter the regular way, but instead they were tricky. They wanted you to look at this and go, L to the negative 1, I don't even know what this means, and panic and get the wrong answer. Okay, so when I teach this and when I teach math, I say it's like the game Portal. And negative 1 has a little gun, that's what the negative is. And it shoots the fraction bar, makes a little hole, and it drops it down to the denominator. So it's a portal gun that only you can use once, so you can't shoot the walls or anything, you can only shoot fraction bars. It's fraction portal. Okay, so that's what that is, so you know what it is. So that is 100, the density is 1.18 grams per liter. So, first of all, what we should do is get the volume. We need to change this volume. It's in milliliters, and notice that's liters. So we need to change that. So we're going to start with that. 843 milliliters divided by 1,000, because there's 1,000 milliliters in a liter. But we want this to be the density. So we're going to put in the numerator, our 1.18 grams. So our density is equal to this. And it's equal to 0.995 grams of air. Okay? Everybody good with that? Now, it didn't ask for the density. It asked for the grams, but we can get there because now the mass in grams of the dry air. Oh, we got that there. So we did get the right thing. Okay, so we'll put a little box around. Doop, doop, doop. I was getting ahead of myself again. I was trying to do the next question already. Calculate the mass in grams of the sealed flask itself. Okay, so we've got the sealed flask and the dry air, and we got just the dry air, so what should we do? Add, subtract, multiply, or divide? Subtract, okay? So we're going to do 157.70 from right there minus 0.995 grams equals 156.71 grams. Put a box around it. Okay, now why do we want that? You'll see. Calculate the mass in grams of the unknown gas that was added to the sealed flask. Well, that's easy now because we got the mass, the flask and the gas, and now we got the flask, so what are we going to do? Add, subtract, multiply, or divide? Think about it. we've got the flask and the gas, and we've got just the flask, so what are we going to do to get just the gas? Subtract. Okay, so we're going to do 158.08 grams minus the flask, 156.71, and we could get just the gas is 1.37 grams. Put the box around it. Okay. Moving on. Using the information above, calculate the value of the molar mass of the unknown gas. Okay, so we're going to use PV equals nRT. We know the pressure, they told us. Look back up and you can see it was 750 torr. The volume we got from our flask, but we need our flask in liters, not milliliters. So it's 0.843 liters. Our N is what we don't know. That's our known. Because we have torr, we're going to use 62.36 for our R. And our temperature is 296 Kelvin. We figured that out in the very beginning. So N, if you put this in your calculator, I'd do 750 times that, enter, divided by 62, enter, divided by 296, enter, and it's 0.034252. Okay? But they didn't ask for the number of moles, they asked for the molar mass. So we have to go back, and what was our grams? Draw a little line here. It was 137. 137 grams divided by the number of moles, 0.03425. So it equals 40 grams. Put a box around it. So whenever they do something like that, then they always want you to do the error. They said you were supposed to get 44. Does anybody remember the formula for error? It's what you're supposed to get minus what you got, absolute value divided by what you were supposed to get, times 100. If you do that out, it's 9.1% error. Put a box around it. Okay, now the problem goes on. So that's what these, you're going to have five free responses, and you can see they're long. They just keep adding and adding parts to it. Okay, for each of the following possible occurrences, indicate whether it by itself could have been responsible for the error in the student's experimental result. You need not include any calculations with your answer. For each of the possible occurrences, justify your answer. So, our answer that we got in lab, we'll assume we did this, was less than what it was supposed to be. So, occurrence 1, the flask was completely flushed with CO2 gas, resulting in some dry air remaining in the flask. Could that have caused our mistake? Yes. Yes, it could. Can anybody tell me why? Is CO2 more dense or less dense than dry air? Less. Yes. CO2 is less dense. Okay. And the next one. The temperature of the air was 23 degrees, but the temperature of the CO2 was lower than the reported 23 degrees. So the gas is colder. Is that going to make it more dense or less dense?
More dense.
More dense. So, and ours was less dense than it was supposed to. So is this something that could account for our error? No. No. Cold gas is more dense. Whoops. Hold on a second. You won't notice I drew my G upside down. Okay. All right, let's try the next one. Describe the steps of a laboratory method that the student can use to verify the volume of the rigid flask really is 843 milliliters at 23 degrees Celsius. You need not include any calculations. So what do I do with my flask? Here it is. Okay, so here's a flask. It says right here that line is 225 milliliters. If I wanted to check it, what could I do to check and see if it's really exactly that line is 225 milliliters? Something real easy I could do.
Pour it in a bigger thing, instrument.
A better one. What's something more precise that we use in lab? A graduated cylinder. So very good. All I would do is pour it exactly to the line of my flask, then pour it in a graduated cylinder and see if it's right. So do you see how this very last part of this AP question was pretty easy, and you didn't really even have to do any of the rest of the problem to get this one right? The test is like that. So it might have hard parts and then easy parts. And if you missed everything else but you answered this, you would get credit. You would get some points. So don't give up. Don't think I don't understand the first part. I'm just going to skip this whole question. Read it all. There might be part of it you can do. And once you write part of it, you might calm down a little bit and you might realize, oh, well, I could do a little bit on this one. Oh, and there's a very good chance that halfway through a problem you can figure it out. Okay? So don't just skip it or anything like that. So this one, so we're going to fill it with water, pour it into a graduated cylinder. Okay, that was an AP chemistry question. How do you feel about it? A real question that was on a real test. Think you could have done it, or part of it, or if you practice a bunch of them, maybe you can get all right at it? Okay, one application of the ideal gas law is a situation involving stoichiometry calculations where gases are consumed or formed. In an automobile airbag, the chemical reaction that takes place to fill the bag is the decomposition of sodium azide, NaN3, to produce sodium metal and nitrogen gas. Calculate the volume of nitrogen gas, so that's my question mark. I'm going to put that's produced at 25 degrees Celsius. What should I do very first? Change that, right? How many kelvins is it? 295, right? 290, 273, 3 and 5 is 8, 298 Kelvin. And 1.1 atmosphere, that's the pressure from the complete decomposition of 75 grams of sodium azide. Okay? So here, I'm going to write down what I know, which is 75 grams of this. What I don't know is I want to know the volume of nitrogen gas. I want the liters of that. Because I have grams, what do I need to go with it? Molar mass, which is 65.02 grams. Because I have liters, what goes here?
22.4.
22.4. And what is my mole ratio? 2 to 3. Okay, so now I can just do the problem. Start with what I know. What I know is 75 grams of that. Sodium azide. I'm sure I'm saying that right. So I push grams to the bottom. 65.02 grams. That's grams per mole. That 1 mole goes on top. The unit mole goes on bottom. The number that goes with it is 2. What's on the other side of the fraction bar is 3. Oops, my sweater's getting in the way. 3 moles. Okay. Now the book has a stop there. And so we would do 75 times 3, enter, divide by 65.02, enter, divide by 2, enter. And it's 1.7 moles. Okay, but normally, what would we have done in honors at this point to get the leaders? We'd gone around and multiplied by 22.04. So so if we did that, that's how we would do it in honors. But they wanted us to use PV equals nRT. So that is, my pressure was 1.1. My volume is my unknown. My number of moles that I calculated above is 1.7. The constant is 0.08206. And the temperature is 298. And if you do that all out, you get 38 liters. But do you know what? If you take this and multiply it by 22.4, what you also get? 38 liters. Because it just all works. There's more than one way to do it. And I think I would just do it by multiplying by 22.4 and gotten 38 liters. But you can see why they did it that way, because they wanted you using the ideal gas law. Okay. Come on. Scroll. There we go. Okay, Dalton's law of partial pressure. Do you remember that one? Anybody remember what Dalton's law was? What is it? P tot equals what?
P1, P2.
Yes, P1 plus P2 plus P3 ... So, what are we doing? Add, subtracting, multiplying, or dividing. What are we doing? Adding. So the sum of the pressures added up, the Dalton's law of partial pressure states the total pressure of a mixture of gas is equal to the sum of each pressure alone. So there's one thing you can do with it. So when we had this in honors, I would give you all but one of these, and you would solve for the other one, right? So we want to make it a little harder, apply it a little bit different. And one of the things they want you to do is mole fraction. So you can always find out the fraction of something, the percent of something, by dividing the part by the whole, right? So how they make this problem a little bit harder is that you might have to figure out the mole fraction, which is the moles of compound 1 divided by the total moles. So that's something they might add to make it a little bit more difficult. So what is the formula? It is that X equals, so the moles is related to the pressure directly. So just like you could do this mole fraction where it's moles divided by the total, you could do the one pressure divided by the pressure total. And these ratios are equal to the same. They are equal ratios. Okay, so now let's apply it a little bit. A mixture contains equal masses of oxygen gas and helium gas. The total pressure of the gas mixture is 2.07 atmosphere. So we have, stop that, we've got pressure tot. All right, there we go. What is the partial pressure of each gas? Okay, so we are not told the number of grams. So what we do is we just pick any number we want, and the number we want is 32 grams because it's the molar mass of oxygen and the molar mass of helium-4 goes into it nicely. So sometimes you just have to pick a number, and you want to pick one where the math turns out nice. Okay, so for this, we don't need grams, we need moles. So we need to convert them. So for the oxygen, oh, come on, write for me. My sleeve is nowhere near you. Let's see if I switch it to erase and then back to draw. Maybe if I pick a new color. What about if we switch to orange? Ooh, let me dot. Okay. So first I'm going to do oxygen. Oh, it won't let me write. Come on. Maybe if I scroll. Sometimes this scrolling will help. Because sometimes when it's at the bottom of the page, like this, it doesn't like it so much. Try it again. Nope, not letting me write. Let me see if I can mess with it over here. Sometimes that works. Oxygen. Now we're going to write helium. Let me write over here at least. Ooh, it's hard to write with the mouse. Okay, now let's see if he'll let me write on it. No, I'm going to close it and reopen it. Sometimes you have to turn it off and turn it back on again. All right, let's see if it will do it. Ooh, let me dot at least. Okay, so oxygen, I'm going to convert, I've got 32 grams. I'm going to divide that by 32 grams per 1 mole. So that equals 1. And now I'm going to do the helium. I've got 32 grams of helium. And I'm going to divide by 4 grams per mole, because that's the molar mass of helium. And I get 8. So how many moles do I have total? 9, right? Everybody followed that? So now I want the fraction. My oxygen, I've got 1 out of 9. And for my helium, I've got 8 out of 9. Okay, and that equals 0.111, and this one equals 0.889. So now I can multiply my moles times my atmospheres, and I can get the partial pressure of each gas. So I'm going to take this and multiply it by my atmospheres, 2.7. And I'm going to take this and multiply it times my atmospheres, 2.7. And this is going to tell me the pressure by multiplying the moles times the atmospheres. This one is 0.3 atmospheres. And this one is 2.4 atmospheres. And those are my answers. What do we think about that? A little bit complicated, but not too bad, is it? We're following it? A little fancy. That reminds me of problems that they like in algebra. You know those problems in algebra where 2 people are rowing in a stream and the current has a certain force, and they row for a certain amount of time. Remember those algebra problems? The rowing in the river algebra problems? For some reason, the way you have to get the fractions like that, it reminds me of the rowing in the river algebra problem. All right, can I scroll it up? We all good? We good, Melanie? Almost. Yes? No? Everybody else? Okay, I'm scrolling. All right, so here's another one, very AP kind of problem. We've got 2 flasks. One is 10 liters, one is 4 liters. In the 10-liter flask, we have hydrogen gas. In the 4-liter flask, we have methane. They have a valve between them, and we open it up, letting them mix. Once they mix, how many liters do we have? 14. Okay? Another thing we have is we have a temperature. We have 25 degrees Celsius, so we probably need to change that, right? To 293 Kelvin. This is some work. And so what we're going to do is we're going to do Boyle's Law twice. Do y'all remember Boyle's Law? P1V1 equals P2V2. So we're going to do it once for the hydrogen gas. Okay, so the hydrogen gas, we started with, it was at 3 atmospheres, and its volume was 10 liters. Then we have our second pressure. We don't know what that is, but our new volume is 14. So we can solve it, and the pressure is 2.1 atmospheres. Okay, now we're going to do it for the methane. Okay, so it started at 4 liters at 2 atmospheres. 2 atmospheres, and it was 4 liters. The pressure is what we're solving for, and once it's added together, it's also 14, and it equals 0.57 atmospheres. So what, and according to Dalton, what do I do to these pressures to get the total pressure? Add, subtract, multiply, or divide? We add them, right? So we're going to add these up, and our total pressure is 2.67 atmospheres. And we're going to round that to 2.7 because of like sig figs and stuff. Okay? So that was the first part. That's the first question. Ta-da. Calculate the mole fraction of each one. If you remember, you could use pressures instead of moles. So we can say X of H2 equals its original pressure, 2.1, divided by its final pressure, 2.7, and we get 0.78. And then we can do the methane, XCH3. Okay, it's 0.6. I just rounded that off. Divided by the whole the pressure of 1 divided by the whole thing, 2.7, equals 0.22. Okay, All right, so that's it. Put little boxes around it. There's another way you can do it that they show you in the book also, if you want to do it, if you want to see more than one way to do it. Okay, so this is a lab experiment. Then when I read it, I thought we could do this, but I think it's too dangerous. So I think we cannot do this because it's got emptying out a whole thing of butane, a lighter. And if there was a spark, that'd be a pretty big explosion, wouldn't it? So I think it's too unsafe. But it's so easy, okay? So what it is, you take a butane lighter, weigh it. And then take it underneath water and push the button, and it'll bubble out all the butane. Well, you can catch it by taking like something glass and filling it up with water and pulling it up. Let the gas bubble up, and it'll push the water out. Can you imagine that? This is the underwater displacement method. So that's what they did. They used to collect the butane gas in a tube by water displacement. The temperature was 22, and the pressure was 755.0 mercury, and millimeters of mercury. And after experiment, the mass of the lighter was recorded at 22.03. So they weighed the lighter before and after. Let me see. Okay. Then it says, once the experiment was complete, the height of the collection tube. I skipped something. Nope. We don't have to do all that math? Guess not. Okay. So at the end, it says it was adjusted. So let me explain this to you. Okay, so everybody remember when you were a baby and you took a bath and you had a cup of water and you took the cup and you filled it with water, and then you pulled it up upside down, and you pulled it up, and you pulled it up, and then you broke the surface, and all the water came out, and it was lots of fun. Remember that? And then you took the air cup, and you squished it down in the water, and then you turned it over, and it bubbled, and that was fun too, right? You remember all of this? Okay. And then you took the water, and you started to drink it, and your mom said, no, we don't drink bath water. You remember this day clearly when you were a young scientist working with gas laws. Okay, when you took your cup and you squished the air down in the water, do you think any of the water vapor could have gotten into that, could have gotten squished into that air before it got turned over? Do you think that air could have been more moist? okay? And as we took our cup and we went deeper and deeper and deeper in the bathtub, was that air squished more or less? Was the pressure more or less?
More.
It was more, okay? So now it's saying that when we did this with our butane, we had our butane under the water and we let it out. It bubbled up through the water, probably getting a little water vapor mixed in with the butane, and then it got into our column and it displaced the water. If we took our upside down column of gas and pushed it deep down, it would get squished and the volume would be different. So instead what it's saying is that you take your column and you pull it up where it doesn't break the surface, but where above the surface of the water is all gas, and below the surface of the water in our tube is all liquid. We're equalizing the pressures here. So why are we doing this? And it is to make the pressure the same inside and out. Because we're going to do math. If you do math with this, you can't have the pressure changing. You need to know what that pressure is. And we want it to be the same inside and outside this tube. Okay. Use Appendix B on page 1158 to determine the vapor pressure of water under the conditions of this experiment. So what this is just a chart. You look up at 22 degrees Celsius and they tell us the vapor pressure of the water is 19.83 torr. Remember I told you some of the water vapor probably got in with our butane? Okay. So now use that number and calculate the partial pressure of the butane gas that was collected in the experiment. So in our tube, we've got mostly butane, but we got a little water vapor in there too, and we want to know what the total pressure is. Well, we know the total pressure because they told us, and we equalize it so we know it was the same inside and outside. So it's 755 torr. And we know the pressure of the water. X is the pressure of the gas that we don't know. But we know the pressure of the water because we looked it up in our book. So now we can solve for X. We just subtract 1983 from both sides. And the pressure of the gas, of our butane gas, is equal to 735.2 torr. Draw a box around it. Doop. That's not too hard, is it? Okay. Let's go with the problem. Okay. The volume of butane gas collected was 100 milliliters. Isn't that convenient? That was such a nice number. Calculate the amount of butane gas in units of moles that was collected in this experiment. We've got its pressure. And now we want the number of moles, we want the N. And N equals PV over RT. So it is rearranged. So our pressure is 735 torr. Our volume was 100 milliliters. What's that in liters? 0.1 liters, that's right. Divided by R. And we are using torr, so that's going to be 63.36. And then our temperature, we figured that out in the beginning, 295 Kelvin. Multiply and divide, and the answer is 0.0040 mole. Put a box around it. Okay. Calculate the experimental value for the molar mass of butane. So we've got our 2 grams, we've got 22.24 grams minus 22.03 grams, so it's 0.21 grams. And then the molar mass would be, grams per mole, so that equals 0.21 divided by what we got for our moles, 0.004 moles, and that equals 53 grams per mole. Now, whenever they get you to do that, they always want you to compare it and see if it's right or not. So the molar mass of butane equals 58.12 grams per mole. And we'll do the error, what you were supposed to get, 58.12, minus what you got, 53, divided by what you were supposed to get, 58.12, times 100 equals 9%. They really like that 9% error, don't they? So do you think you can do a problem like that? We'll do a lot of practice problems. And then you'll remember, oh, when it's like this, I do this. When it's like this, I use density. When it's like this, I subtract. Okay, so this is the kinetic molecular theory of gases that supposedly you learned. Yes, Mr. Atticus?
Back up. Can you explain to me where you got 22.24 minus 22.03 from?
That was our butane. Go back up. So we had our lighter, and then we got the amount afterwards, 22.03. So it is the lighter with the gas minus the empty lighter. So it makes sense. Any other questions? See, that's why I said we could do this, couldn't we? But I'm afraid we might blow something up, so let's not. But like, we could get lighters, we could do this. I've got those tubes in the back, I've got the little green things. All we would need was the butane lighters. But I bet they're illegal at school, don't you? Are cigarette lighters illegal at school? Probably, I'm thinking probably so. But it would just be such an easy lab to do. Okay, gas molecules are in constant kinetic molecular theory, you learned this in honors. Probably learned it in physical science. Gases are in constant random motion. That's right. The combined gas volume is important or not important? Not important. It's negligible is what it says. Negligible. The attraction repulsion forces of the gases are important or not important? Not important, negligible. You remember this now? Collisions are, they bounce off of each other. What do we call that? It starts with the E. Elastic. Yes, I heard somebody remember it. It makes me happy. The average kinetic energy does not change at the same temperature. The average kinetic energy is direct relationship to absolute temperature. At the same temperature, all gases have the same average kinetic energy. Does this mean they're all going the same speed? No, it does not. All right, the diagram at right can be found on the bottom of page 403 in your book. It shows the distribution of molecular speeds for nitrogen gas at two different temperatures. True or false? At a given temperature, each molecule in a sample of gas is moving at the exact same speed. False. Some are going faster, some are going slower, and it's not even the average speed is temperature, it is average kinetic energy. Okay, true or false? As the temperature of a gas sample is increased, the average speed of the gas molecules increase. True, yes, very good. Okay, true or false? The distribution curve tends to broaden as the temperature is increased, indicating that the range of molecular speeds increase at a higher temperature. So see, it's this one is a higher temperature than that one. Do you see how, does it look broader?
Yeah.
Yes, so that is true. that as you increase the temperature, you get more variety in the speeds. Okay? The average kinetic energy per molecule of gas is equal to 1/2 mv squared. Always kinetic energy, where m is mass and v is velocity. This information helps us compare the average speeds of different gases at different temperatures. How should the following gases be arranged in order of increasing average speed at 298 Kelvin? Okay, so this is what you got to get in your head. This is the big thing to remember, is that lighter particles travel at faster average speeds. They all have the same average kinetic energy because they're at the same temperature. But the kinetic energy is made out of speed and mass. So the little ones have to move faster to make up for the fact that they're lighter. Can you get that in your brain? Little ones move faster, big ones move slower, but they are at the same temperature. They have the same average kinetic energy. Okay. So now we're going to put them, lighter particles travel at faster speeds. Which of these is the biggest?
CO2.
CO2. So we're going to write slow down here, and we're going to write CO2, and because this molar mass is 44, then which one is next?
Nitrogen.
Nitrogen at 28, N2. Okay, and then what would be is next? Oh, the last one is neon, because it has a molar mass of 22.2. So this is the fast end, and that's the slow end, but they all have the same kinetic energy, but average kinetic energy, because they're all at the same temperature. What does the diagram tell us about the relationship between molecular speed and molar mass? So we got hydrogen and we got oxygen. Which one is the lightest, hydrogen or oxygen? The hydrogen is right. So it is the lightest. Oxygen is the heaviest. Okay, which one is fast? Hydrogen is fast. Which one is slow? Oxygen. Okay. For gases, there is an inverse relationship between molar mass and average molecular speed. All right, that's all we have to know about that. And that'll probably be on that will be a test question on the AP test. They love that. They love asking you about that. Okay, effusion and diffusion. You know these things, you just might not know their names. Effusion is a gas escaping from its container, and diffusion is gases mixing. So a long time ago, when I first started teaching regular chemistry, there was a lab where you're supposed to take a bottle of perfume and open it at the teacher's desk. And then the students would raise their hands once they could smell it. And then you could actually see the effusion. As people raised their hands, you could see that the gases were escaping from their container, and then they were diffusing, they were mixing with the air in the room. It was terrible. We opened that thing, we were getting headaches, we even turned on the vent in the hood, we couldn't get it out of the room. That's one of those live and learn. Don't do that demonstration, it was awful. Okay, so that is our thing. Okay, so now, even though quantitative calculation involving Graham's law is not likely to appear on the AP chemistry exam, it's still a good idea for you to be able to use this equation if they gave it to you. So a certain gas has a rate of effusion that is twice as fast as that of methane. Calculate the molar mass for this gas. So R is the rate of effusion, and the rate of one gas over the other one is equal to it flipped square rooted. Big M is molar mass. Okay, so now, this is a 2 to 1. It's a 2 to 1, it says. It's twice as fast. So the rate of X, we don't know what that is, over the rate of methane, we were told that one was methane, is equal to the square root of the molar mass of methane over the molar mass of X. Okay, so we could set this up. We know this is a 2 to 1, and 2 divided by 1 is 2. is equal to the molar mass of methane. We can look that up. It's 12 plus 4, so it's 16, divided by our unknown. Now, how do I solve this equation for x? How do I get x out of the denominator when it's square rooted? What do I do first? What do I do first? Square both sides. So I'm going to first square both sides, and that'll get rid of the radical. And now what do I do to get x by itself? I'm going to multiply both sides by x to get it out of the denominator, and then I'm going to divide both sides by 2. So x equals 4. 4 grams per mole is its molar mass. What element has a molar mass of 4 grams per mole? I heard somebody say it. It's helium. So that's a real fun little problem because it had a little mystery that we were able to solve. We got its molar mass and we were able to tell what it is. All right, next. Real gases, deviations from ideal behavior. So, real gases don't always follow what we said in the kinetic molecular theory. Gases tend to experience the largest deviation from ideal behavior under conditions of high pressure or low temperature. And it's because of attractive forces come into play between the molecules. The particles of an ideal gas are assumed to occupy no space and have no attractive forces. However, the particles of a real gas, of course, have volume and they can experience some forces. Explain why under conditions of high pressure, the volume of gas tends to be slightly greater than the value predicted by the ideal gas equation. So look at, this is low pressure. They're all spread out. They have no effect on each other. The volume is negligible. But if we squish them down enough, they start taking up a big enough percent of that container that the volume is something to be considered. So under high pressure, the combined volume is no longer negligible. Okay, next one. Explain why, under conditions of low temperature, the pressure of a gas tends to be slightly smaller than the value predicted by the ideal gas equation. So now it's very cold. The molecules start to move faster or slower if it's cold? Slower. And then, so now they start to go slow and have attractive forces. They stick together and they won't collide with the walls of the container as much. And so that makes less pressure. In general, gases tend to experience larger deviations from ideal behavior as the strength of their intermolecular forces increase. For this reason, which of the following molecules is more likely to show a deviation from the ideal gas behavior? Hydrogen or water? Which one is going to not be as ideal? Any guesses? Water, why? Because it's polar, yay! That makes me so happy. It is the water because it is polar. So it's going to have positive and negative ends that's going to attract each other. Does that make sense to you? All right, that's it. Done. How'd we do? Oh, look at all. Y'all are so, we always finish faster with you guys. All right, science is great. Like, share, subscribe.